Hello everyone, my name is Chris Lewis and my partner here is Jonathan Meyer, and we're going to be giving a talk called Where's My Camera? And that's my shorthand for saying extrinsic calibration of cameras. We also do intrinsic calibration. So several years ago I built a system for doing extrinsic and intrinsic calibration, and it was designed for industrial applications. And the idea was that it would be part of some killer ROS application on a factory floor, and whenever the cleaning people came in and accidentally bumped your camera, the system would recognize it. This calibration system would then take over control of the robot. It would move it through a bunch of poses. It would recalibrate everything and have you back up and running with no user input. And so I wrote this really marvelous, actually it was quite awful, node that would do pretty much every kind of calibration as long as you configured it well. And it was a massive effort to configure it, so pretty much nobody used it except for me. And it had launch files that you had to configure in very special ways to get the system to work. You had YAML files that you had to define parameters that had virtually no documentation. So there was a great segue from Dave on that you have to document things. It had all kinds of scene triggers. You had to set up every scene for which cameras were going to see which targets and how they were going to trigger the camera to see that target within this region of interest. And you could do all those things if you defined the YAML file exactly right. You had to define these cameras that had ways of telling them not just that the scene was ready, but that camera was actually being triggered. And you had these transform interfaces because it's pretty difficult to change a URDF on the fly. You can't do that. So we had to add a mechanism for being able to do sort of interface with, be able to change transforms in the same way that the camera info manager allows you to update the intrinsic parameters. We need to be able to do that in order to do this extrinsic calibration, to have your robot calculate where your camera is and then have it update, and the next time the system comes up, it should be where you calculated the most recent time, not where it was when they first installed the system. Okay, so what we tried to do is to divorce. We want to make this much simpler and easier for anyone to use, not just me to use. And so we divorced all the calibration from all this motions and triggers. And we made it into a very straightforward, what I think is a straightforward, it's service-based. It actually should be an action-based. Having used it over the last few months, it should be an action because you push the button and everything locks up. So we will be moving it to an action-based methodology. It's not a very difficult thing to do. Basically, you start it. We have a very simple GUI, and we have all our different calibrations. We took all the standard calibrations that people do. They might have a camera they mount on a wrist of a robot. They might have several cameras around the work cell. Anyway, so you can imagine we basically tried to rewrite each of one of these as an individual node, so you don't have to do any configuration for that node except for telling it which camera and certain key pieces of information, but it's much easier to define, much easier to document what's going on if there's only a few things that you have to pick between. So basically, this is also helping for industry where we try to field a robotic system. And a lot of times they don't want us to just take over control of their robot and tell it to go here and there and everywhere because, as we know, it may make it move very close to things, and it's somewhat scary. So they'd like to have their PLCs saying, okay, I've moved the robot to where I want it. Go do your observation now. I'll move it again, and you can do another observation. So essentially it's a service call based. Every time we want to take a picture, you just call the service to say, hey, take a new set of pictures, and it'll collect those observations. Once I give you enough observations, then you can tell it to run. It will run. It'll tell you how well it worked, and then you can either save those results or not. And anyway, so let me move on. Yeah, so I said we created dedicated nodes. So for intrinsic calibration, which is calculating the parameters which adjust for the distortion of the lens, we have a rail-based system that uses a linear rail and moves the camera back and or the target or the camera back and forth on a rail. We also have one that works on the robot, so if you don't want to take your camera off the robot to do your calibration, it'll work right on the robot. It turns out the rail is a little bit more accurate, but you can do it on the robot. It doesn't matter whether the camera's on the wrist or whether the target is on the wrist, moving it around. It works just as well. We also do what we call wrist calibration. Again, either the target is in the hand or the camera is in the wrist of the robot or mounted on the tool. Those are very similar things. And we do stereo calibration, again, whether the camera is on the wrist or whether the target's on the wrist, it does the same thing. Calculates the translation between the pair. Okay, so we also added some key features, which are load, which allows you to, if you've gathered a bunch of information, you don't want to spend all the time for collecting this data again, saves it in a file, it pulls it back in and reruns it. But that allows you to run these calibrations without actually having a motion. You can take the pictures just by yourself. You don't need to use the robot at all. You can then load it in and run it and make sure it's going to work. And the last thing is it computes for each one of these different styles of calibration, it computes the covariance matrix. And the key issue here is that a small residual, and typically with camera calibrations, we're talking about a quarter of a pixel error on average, is no guarantee that you have a good result. So what you need to look at is the covariance matrix. And I know it's a little complicated, but once you have designed a calibration routine that you want to work every single time, you have to look at those things. And we're going to talk about that a little bit more later. And the key question is have I taken enough data? And has anybody used the OpenCV and ROS thing where you move it around? So the little arrows get green, and you're like, oh, that's great. But if you look at the results, they're not very consistent. Right? I think everybody's experienced that, and I can point to some reasons why that might be. So to make it even easier, we've now added GUIs in that same GUI that I talked about before in RViz, where you can just click on the buttons and have it say, take a new observation. So now you can use Move It to move the robot around, and then just click, oh, take another picture right here. This is a good one. And you can then see you can display your images, and it will show you that you've got a good observation, and then you can finally run it and then save the results, and it will move the transforms around, and everything's good. And we added one extra little piece here to make it even easier, which is a completely different node and another GUI. The yellow box is about this, which allows you to save all those motions in a file, save all those joint commands, and then it'll just execute all of them one by one and pause at the end of each one and take the picture that you tell it to take. Okay, so here's the example of the intrinsic calibration, and in this case, we're taking all planar pictures. Somebody might complain about that. If you are interested, I can describe why this is an okay thing to do, but we have to move the camera once. So we're only computing two different poses, the pose between the camera and the starting point in each case, and then the axis along which that rail moves in the target's frame. And if we do those two, we get very good intrinsic calibration consistency. And essentially think of that as a sort of a frustum of data going back into space. So we're seeing it's almost like a single target that has a lot of data. And we do the same thing in terms of intrinsic calibration using a target on a robot. So it's a different node, different package, or not a package, different node. But it has the same exact type of service calls, just a different base name of what this is. It says take a picture, and then you have to move the robot, and it takes the picture again and add all the observations you want. Compute your covariance whenever you're ready, and then see if you're good and add more pictures if you're not. Okay, so I want to talk a little bit about repeatability and accuracy. So we do these calibrations. You take maybe 100 pictures, and you get a quarter pixel error on your results per observation. But then if you do it again and take another completely different set of 100 pictures, your focal length or your center points will be off by many, many pixels. And yet when you use your system, say it's a stereo system, we can measure at a meter distance with a stereo pair with a fairly normal baseline. we can measure less than, I want to say, a thousandth of an inch because I know that unit, but this is the metric system, so I converted that, and it's anyway. The point is, it's very accurate to measure the configuration. Yet the focal length changes quite a bit, and that mounts to the cameras in a different spot, but the accuracy of the localization is the same. So I'm going to run out of. So we just tried to take to figure out what was going on here. We tried to create a target that had data everywhere. Did we need more data or not? Well, we said, well, let's take as much as we possibly could and do it in simulation. And this is looking down a tube of data that's on a grid and we just said, we'll just simulate this and just see what we could find. And what we found was that even with all this data, we have essentially a redundancy in the model. And I'm going to kind of gloss over this. The idea is that the result is that we probably shouldn't be using such a complex model for intrinsic calibration because there's several different cameras that all are equally as good, just have a slightly different a difference between the focal length and the radial distortion, for instance, or if you can move the center, and then the P1 and the P2 terms, which are decentering distortion. They're sort of the same as moving the center. So those are essentially redundancy in the model. Okay, I'm going to skip this one. This just shows that I'm going to demonstrate a quick stereo calibration here. What I'm computing is I've basically hit the run button. I've saved a bunch of poses, and then I hit the run, and it's basically just taking a whole bunch of pictures, and you can see all the pictures in the side there. And what we're computing is just the transpose between the two cameras, and then we're using the forward kinematics to the target, roughly, and computing also the transpose to essentially to the target as well in this calibration. And it's not very interesting. You just see a bunch of pictures being taken, but the idea is that this is a single node. It's dedicated just for doing stereo calibration. Okay. And so we do camera on the wrist. This computes the transform between the tool and the camera, which is mounted on the wrist, and the transform between the base of the robot and the target. So you just throw the target down on the floor or mount it someplace in your work cell. You define a bunch of poses where you can see the camera, but you have to do a lot of different poses, and this is where it's critical, again, that you check that covariance to show that you don't have correlation between your measurements. And this is the same exact thing, except we've exchanged the wrist. We put the target on the tool, and the camera's mounted in the work cell. Again, I'm going to hand off the rest to Jonathan.
Thank you. I just wanted to plug a package that we've sort of been working on at Southwest. It's in the same vein as industrial calibration, and it's sort of informally called Robot Cal Tools right now. And what it is sort of, you know, how Dave talked about ease of use and documentation and things like that. So Chris has started on this journey to make it easier to use a lot of the industrial calibration tools. And so from my perspective, as somebody who puts a lot of robot systems together, there are cases, like Chris mentioned, where I have little control over the system that I need to calibrate. And so what Robot Cal Tools does is dives deep into industrial calibration and pulls out the core cost functions, the sort of optimization core that allows you to perform calibration. So, like I said, industrial calibration works well, but it needs an ecosystem, right? There needs to be camera info managers. There needs to be somewhere to put your calibration results. And maybe you don't have that. And so I started this as sort of a learning experience, and the focus was to make an API that was just pure functions, right? Functional programming, woo. It doesn't make any assumptions about the data, your data collection procedures, or what you do with the answers, right? It pulls out all these common cost functions that Chris has written, And it's hopefully useful either for you who's writing something custom, right? You have a weird camera or a LiDAR camera configuration that you think you can do better. Or if you're just interested in learning, right? Because what you'll find is that most of these things can be reduced down to about 20 lines of code, especially with tools. So at its core, the only dependency is series and sort of transitively eigen. If you guys aren't familiar with series, by the way, big shout out to Google and the people that wrote that. It is the best piece of open source software I've ever used, and it makes so many cool things possible. But just to give you an idea about the API of RobotCalTools, right? There's a struct that is the problem. You choose the header that describes your issue. You fill out a struct that it says, this is my camera data, and here are my correspondences. And correspondences, just real quick, are, I see a point in 3D, and I know what pixel it ended up at. It's that matching, right? Sometimes you have 3D to 3D, but most of the time we're working with pinhole cameras, 2D sort of models. And then you call the optimize function, and you get a result back. Right? And the result will have things like the average residual and the cost and things like that. And you could even, hopefully, eventually plug it through sort of the covariance analysis and say something about whether you had a good result or not. There's also a lot of tools for handling different kinds of, or a few different types of targets, usually using OpenCV stuff, but you don't have to use that if you don't want to. And there's a real emphasis on documentation. There's lots of wiki articles describing what the targets look like, conventions for coordinate frames. All the headers are absolutely documented out the wazoo. But there may be problems, and if you have any, please let us know. So, Chris?
So this slide tells you where you can find the tools. They're not quite all put together yet. As he mentioned, we're going to try to combine these two all in under industrial calibration. Also, I have the recent, these fancy new nodes that I've made have not quite made it in. I thought I'd have some time to have, if you want to find them, look for the branch on my repository with about 500 commits, and I kid you not. And by the way, if that is interesting enough for you, we're hiring. And our future plan, of course, is to integrate this into industrial calibration, and we want to provide tools for experimenting with kinematic calibration. If you think about the calibrating where the camera was on the wrist or where the target was relative to the robot, that's essentially a kinematic calibration. So we'd like to advance these same concepts to use cameras to calibrate the kinematics of the robot. We'd like to provide more experiments with laser profile scanners and LiDAR sensors. And of course, we need to do a lot of documentation for what we have already so that people will use it and help us make it better. Thank you.
Any questions for the speakers? Yeah, we've got one headed to the mic.
So, thanks for the talk. You just alluded to kinematic calibration at the very end of your talk just now. Do you plan to collaborate with the robot calibration package that Mike Ferguson was working on right now?
Yes, I'd say so.
Sure.
Yay!
I tend to work in a very heads-down mode, so if somebody will point me in the right direction, I can then work in a head-down mode at that direction.